I'm very happy to show some of our recent research. Some of the project has been a while, but um, I have to say this is an unusual topic in, let's say, chemistry, or especially in organic chemistry section. So I will go to the traditional way of doing CHEMTalks, starting by how I kind of started this idea based on my training. So I started my study in South Korea in Sungkyunkwan University in 2001, and after my bachelor and some time off, I did a master with the same supervisor, Professor Jiwoong Lee. I worked with the ion liquids and basically methodology development in asymmetric synthesis. So I was working with the enantiomers, checking enantiomer selectivities, and making catalysts. And with that information, I moved to Germany to do a PhD with Ben List. At the time, he was he was just a normal person, but not anymore, because he got the Nobel Prize last year in chemistry with his contribution in organic catalysis. It was a really different environment, of course, in Max Planck Institute with the support and infrastructure. But core idea I think I got from the MPI is that if you have certain persistent, I think anything can be achieved. And one thing, after my PhD defense, actually Ben asked me, so what is your goal? And then I said, I want to save the world. And then he said like, I think it's too late. So I was like, is it too late that I'm, not good anymore, or is the word is too late to save? He didn't answer that question anymore, and then I have to keep it as a driving force to do something, that can contribute to the society. So then I moved to a little bit warmer side of the world, to the Weizmann Institute with Raphael Klein. He is still in Israel, but he will move to Vienna soon to move his group. I worked with self-assembly, some nanoparticles, and then responsive systems, but also I was interested in using CO2 as a stimuli, or some, let's say, small molecule to control certain chemical or physical system. And then I was interested further in some material chemistry, so I moved to Berkeley, worked with Jeff Long for a year and a half. So, and we worked with the CO2 capture, increasing and modifying more meta-organic frameworks to scale up, and then also more sustainable way of making porous organic polymers to do some interesting chemistry and gas capture. So I moved to then 2016 to Copenhagen. I started working with new ideas, trying to make some distinction from my PhD and postdoc. And now we are focusing on basically carbon dioxide, how we utilize them or capture, and also doing, let's say, traditional organic chemistry, how to control organic reactions with the carbon dioxide. And today I will give you two examples, basically ran by these two gentlemen, Anand and Alexa, working on desalination and CO2 capture chemistry. And then, as you can imagine, why I put this world map upside down is obvious story. That world is full of water, especially seawater. And today's topic is, again, seawater, mainly with the carbon dioxide. So then we need to learn a little bit about the carbon dioxide and seawater. Two things, right? Seawater and carbon dioxide. Seawater is quite simple. You have it everywhere, especially in Copenhagen, surrounded by seawater. But it's not that easy to look at as a simple chemical, because it's mixture of everything and commonly distinct by the total dissolved solid materials, especially ionic species like salts. And around Copenhagen, of course, the salinity, let's say, the amount of the salt dissolved in seawater is not that much. So even I can notice that my son, when he's playing in the canal water, he can just suck up the water and then trying to drink it, because it's not that salty, and maybe it's a little bit tasty. But if you go to Mediterranean or Dead Sea, for example, you cannot even put it in your mouth, because it's very, very, very salty. So there is a degree of salinity. This is important, but also important thing is that what is the salt. So if you look at the composition, chemical composition of the seawater, of course, it's mainly water, 96%. The main contributor in the sea salt is, of course, we know that sodium and chloride, and then sulfate is a little bit more, and then other minor, let's say, ingredients, including boron, silicon, and other organic compounds are contributing to the chemical composition of the seawater. So as a chemist and organic chemist, if you look at this diagram, okay, the seawater is mainly in sodium chloride, so let's focus on that. What about the CO2? So CO2 is a small molecule, and we know that it's a actually inert gas, that for us, it doesn't do anything. Of course, in high concentration, you will suffocate. We use it daily life in organic chemistry lab and other scientific area because we use dry ice. You can use supercritical CO2 as well. Has a reasonable solubility in water and actually higher in organic solvents. Therefore, it provides this ability to do chemistry. It's a little bit complicated because it's a polyphotic acid in the presence of water. And more importantly, it has no dipole moments, but of course, it's quite polar in terms of quadrupole moment. So you can play around for the CO2 capture and so on. And then you can, I can share this information whenever you want, that there are a lot of people have been working on, of course, carbon dioxide in different ways of chemistry and physics to utilize them and try to solve important problems. In our case, we are focusing on, of course, now water, because CO2 in principle intrinsically electrophilic, will interact with the nucleophile. We're talking about, in this case, water as a nucleophile. So how does it work? It's basically controlled by the thermodynamic law of solubility. So Henry's law constant will determine the CO2 solubility in, let's say, surface of the water. In this case, we are talking about the sea. And as you can imagine, the concentration of the CO2 in atmosphere is increasing. I had to change this number every now and then because the number last time I put it in here, another slide, it was April, it was 418 ppm, now it's 9 ppm, and then it's actually increasing to 20 ppm soon. So this is quite surprisingly fast to see that the number is always increasing. Another thing is, as I mentioned, that the CO2 in the presence of water, it will form carbonic acid. Carbonic acid is polyprotic acid, so it has a multiple 2 equilibrium, right? Because CO2 will form bicarbonate. At the same time, bicarbonate will be in equilibrium also with the carbonate. So we have 2 constants. Where do we look at in daily life? You see carbonate, so form of CO2 in solid form in the presence of water and some base or calcite. So we see this material a lot, and some of the anecdotes that we heard, I don't know if it's true, that the Cleopatra was hosting like the most expensive dinner or something. So he brought, she brought some vinegar and dropped her most expensive pearl to dissolve in vinegar as a, demonstration how worthy she was, or that the country was. But what we see most often in the media is that the acidity, right? I mean, the CO2 concentration changes can affect the biodiversity and the structure and biostructure of the whole planet. Why? Because we know this for a long time, since 19th centuries, from one of the person from this institute, this theorem show that the CO2 is in equilibrium with the carbonic acid, bicarbonate, and carbonate. Of course, this is depending on the pH, changing the molar fraction of each component. As you can imagine that right now, the seawater or water that we have is almost neutral, but slightly basic, around 8.5. So the majority of the composition of these 3 series is bicarbonate. of course, now we are looking at what's going to happen if you increase the concentration of CO2 in the atmosphere. So if you look at this beautiful Copenhagen city, we have CO2, we have water, and people are enjoying their life. But at the same time, if you look at CO2 dissolved inside of the water, controlled by Henry's law constant. So we have the constant, and then we have a certain partial pressure of the CO2 in the atmosphere. Once it's absorbed, we will see that the CO2 reacts with the water and then generating one molecule of bicarbonate. Of course, then bicarbonate or carbonic acid will be immediately dissociated with extra proton. This is, of course, equilibrium constant. And this proton will be, again, interacting with the carbonate anion, because carbonate, we have the reservoir of carbonate in the seawater, which will take the proton, generating bicarbonate. So in the end, because of the one molecule of CO2 absorbed in water, we will generate two molecules of bicarbonate by consuming one molecule of carbonate. This means that you are increasing the concentration of CO2 as it is right now, as we speak, then we will make the whole seawater in the planet more acidic. So what can we do? I mean, one thing is that we cannot change the physical, this is constant, and it's an equilibrium constant, Henry's law constant. We cannot change them. So as a chemist, what we can do is we're adding something. And then, of course, people have thought about this by using organic or inorganic base that can change the equilibrium and also even the kinetics of CO2 absorption to the water. And this is something that looks a little bit complicated, but basically same reaction that you have seen from the CO2 and water reaction that generate sometimes carbonic acid and carbamate. Also in the presence of water, you will generate bicarbonate and carbonate species, all in equilibrium in the presence of CO2 and water. Most common structures of doing this type of, let's say, CO2 capture is shown here, MEA, diamine, and DMAPA, that I will show you the structure and relationship to the performance today. They are also most common in CO2 capture because they're cheap, they're accessible. Of course, they are coming from, you can imagine, ethylene, in this case, acrylonitrile, and so on. So you can imagine the scalable synthesis of this kind of material. So one of the ideas that we had at the beginning was using those diamine or MEA and then simply isolate them, because then we can control the solubility of this species in water. And why do we want to control the solubility of water? Then we can actually do something, because if it's too soluble, you cannot recover them. If it's less soluble, we can take it out and then do some extraction and so on, so that we can do some chemistry. That was a very naive idea at the beginning. But good thing is that this amine, after alkylation, still responsive to CO2, so that it generates some sort of surfactant type structure in the presence of salt. So therefore, this is seawater protein, seawater reaction. We see the responsiveness by looking at the conductivity. Also visually, after 1 minute of bubbling of CO2 is completely different. So we check the DLS. There's some particle formation, so it's indicating that we have some new, let's say, aggregates or supramolecular structures. Most important thing at the time was that if you filter this using ultrafiltration, so of course it's an expensive process, you can reduce salinity, because we start with the 35 gram per liter of seawater, and then we can reduce to 3 gram or even 10 gram per liter of salt. We can reject it by simply filtering, but the drawback was that the recovery rate was extremely low. So, we don't get a lot of water. This kind of compound has been utilized in CO2 actually as a responsive surfactant in oil recovery, right? Because when you take out the oil from the oil field, you have to re-inject something to fill up the space. And then, of course, then there are some problems with the pipe, has to be, free flow. So then they add some surfactant with the water. mixing with the CO2 because they are burning a lot of CO2, and the CO2 is actually very good gas to fill up those empty spaces. And then this type of organic material with alkyl chains can do that very well. Now, also, it has been reported in the literature that this type of amidine modified with the alkyl chain are CO2 responsive that can make sort of emergent. So then in this case, water and cyclohexane mixture, let's say two-phase system, can be emergified as a one phase under CO2 conditions. You can do that to clean up the oil, so you can make a CO2 made it emergent, which is a reversible process upon introduction to inert gases. Also, Leclerc from France, he also showed that this type of amines, when they are coordinated to CO2 and they make the carbamate, you can extract sometimes heavy metals. So you can actually capture CO2 while taking out some heavy metals from water as a mean of water purification. Rasmus was a bachelor student and then continued as a master student. And then he did a key experiment because of the CO2 interacting with those kind of amines and showing that this CO2 amine interaction, or let's say CO2 capture, is very reversible. So he showed that the desorption of the process can be initiated around the 50 to 60 degree. And this is a very important feature because if you look at the CO2 capture and direct air capture, most of the energy consumption is coming from the heating the stripping process. So CO2 desorption actually is the most costly process. And Rasmus also made a balloon by himself by blowing the balloon with his own breath, and then showing that this red one is pure CO2, but also the green one, so lower concentration CO2, also works in this system for the desalination. So we thought that this is a nice chemical system to demonstrate the reversibility and capturability at low concentration of CO2. So Alexa took this project further and then really parsed through the system by checking a lot of chemical structures and weight percent and then different composition, and show that in saline water, we can actually compete with MEA, 28% MEA, this red one, and then now with the 80%, so that water lean system. So we can minimize the use of the water while capturing CO2. We believe that this whole system is responsible for the advantages of coming from these aliphatic chains interacting through the hydrophobic interactions by forming aggregates and then increasing the process performance by increasing the freedom of the water molecule, because this is the principle of the self-assembly that we can design and tune the molecular structure, therefore performance of CO2 capture as well. This is another highlight that we tested in many different compositions in terms of salinity and then observed loading, that's showing our MEA system is almost same as a conventional MEA system in CO2 capture in terms of weight percent. So this is close to 9 to 10 weight percent of CO2 captured into the system by simply using this alkylated amines. And this is again confirmation that we can change the alkyl chain to, for example, shorter alkyl chain that doesn't give any effect of the brine or CO2, so that doesn't give any additional advantage like we had with the long alkyl chain attached MEA. As I said, the most important thing in CO2 capture, again, is the desorption. So we want to have energy efficient process for the desorption. One quick experiment in terms of conductivity, we can see that around 50 degrees or 60 degrees, we can start seeing the desorption process. Usually MEA solution is energy intensive for desorption because 28% is the absorbent, and then the rest is the seawater, water. So then water has high heat capacity, so therefore you have to spend a lot of energy just to boil the water at the same time. Since we are having the seawater system and water lean system, we are using less energy. At the same time, the system itself is not that exothermic in terms of CO2 absorption. Therefore, we can do energy efficient desorption at low temperature, which is a huge advantage for the future applications. So we found out that the certain amines, we can do better CO2 capture in brine solutions. Also, it's easier for desorption. But one thing I didn't mention is that everything is in seawater, because we don't want to use DI water or drinkable water, because then you have to compete with the other resources. So the most accessible resources, I think, is seawater. But seawater, again, has a lot of salts and ions. So then we have to think about this ion exchange process, because whenever you have certain ion, it will be exchanged, and then giving a complicated picture of this whole process, because it's not only the chloride you're looking at in the seawater, there are other ions and so on. But of course, if you look at the ion exchange, how it's applied is you have done many chromatography using ion exchange process. Of course, we commonly daily use the ion exchange column for water softening in the lab or in household appliances like dishwasher and so on. But in chemistry, this has been a main production process for soda. So this is a sorbet process to produce soda in 1900, not anymore, but at that time it was responsible for 90% of soda production coming from CO2 and ammonia. If you look at this diagram, it looks a little bit complicated, but I think I can spend a little bit more time here because it's important. Ammonia, of course, is a base. In the presence of water, it will interact with the CO2. So now we are taking this amine as absorbent, doing CO2 absorption. The CO2 absorption will result in ammonium bicarbonate formation. And this is also happening in the presence of sodium chloride or seawater. So then we are expecting ion exchange between these two salts will give you ammonium chloride one side, and the other way we will get sodium bicarbonate, which can be heated up, removing one molecule of CO2, and water will generate sodium carbonate. And in sorbet process, they utilize calcite and then generating calcium oxide by heating it up. So the main energy input in the whole process was this heating process to generate pure CO2. Our case for CO2 capture and desalination is very, very similar, but we are just replacing ammonia to some other types of amines, and then going through the same step, CO2 absorption in seawater, generating ammonium bicarbonate, ion exchange in the seawater, so you generate ammonium chloride. In this case, the key point is that we make amine insoluble in the form of ammonium chloride, that we can take it out from the water, seawater. Other side, we generate sodium bicarbonate, which you can just protonate and generate CO2 by removing sodium ion. So we overall achieve desalination out of seawater while basically collecting CO2. So this is also kind of another way of looking at it, the same thing that we can capture CO2. That you can see the similarity between sorbet process and our diagram. So let's go a little bit fast, because the DESTA at the time tried a lot of things and then finally found out that the certain polymer with the acute chain length, we can achieve salinity going down after bubbling CO2 for some time. This was really breakthrough. And then Anand took the project further with the different types of the polymer, different chain lengths and different alkylation degree, that we can see that overall, this is not just by checking one type of measurement, is conductivity and silver titration and NMR and HPIC mass. So we are sure that we are removing sodium and chloride ions overall gradually during the process through CO2 mediated ion exchange. And of course, sometimes we have to add some acid to remove the sodium ion. In this case, we use polysulfonic acid to recover the sodium ion very easily. It was a little bit difficult to process it, because in this case we are using polymers, so therefore we further developed our process in a continuous flow system. So we took an epoxide-based resin, modified with a diamine, so we generate this amine system, amine-modified resin system, sorry. And then if you look at the data of the sodium and chloride recovery rate of the bare resin, of course, there is no action of Cl minus or chloride capture. But when you have this amine immobilized in the system, then we will see the action by looking at this setup, very simple setup. We have the CO2 inlet, we have the feeding solution circulating through the static pump, and then we collect the water for the further analysis while measuring the chloride concentration real time with the chloride selective electrode. So if you look at the breakthrough experiment with the chloride ion, so when there is nothing, just amine in the resin, the chloride just comes out plainly. I mean, there's no interaction between chloride and the resin itself. So we can recover quantitatively everything in the conditions. But if you look at this arrow and then bubbling CO2 to the resin, so therefore we are activating it. Then after that, if you flow the seawater solution, in this case diluted up to 5 grams per liter solution, then the chloride doesn't come out because the chloride is stuck inside of the resin through the ion exchange. So then using the same concept, that now we are looking at continuous flow experiments, right? The background that chloride is just coming out when there is no CO2. And then after CO2 introduction, and then flowing the sodium chloride solution, there is a gradual ion exchange. Therefore, the significantly lower concentration of the chloride is coming out. This is just due to that the fact that we are adding more and more just to make sure that everything is saturated. We are just pushing more sodium chloride solution into the resin. That's why we see this Cl minus coming out. After washing with the DI water, of course, we can clean it up. And then, of course, then there's nothing coming. But when you add some base, KOH, then we can also recover or the captured chloride as a form of potassium chloride. For the column, the integration looks different because we just changed the rate of the process here. So this is just a demonstration that is continuously producing chloride removed water drop by drop, overall close to 1 to 2 liters per hour of the system. It's a common thing that since we are talking about the desalination, we have to mention about how much energy we are using. I have to be honest with you that all these blue ones are coming from 35 grams per liter seawater solution. Just to show that with our experiment coming from 3.5 up to 15 grams per liter brine or brackish water desalination, we are showing some comparable energy consumption only based on the regeneration, which I didn't show you so much, but hopefully next time I can talk about this process more. In conclusion, so we have shown some interesting phenomena of CO2 in seawater. So we can capture CO2 in brine solution. By using the same system, we can actually use this brine CO2 capture for desalination. Then probably everybody is wondering, what about the flue gas or direct air capture? Of course, that's our direction, that we want to use low concentration CO2 for the CO2 capture. So with that in mind, then our next goal is actually more interesting because now we will capture CO2 while desalinating. So simply by having the similar system and doing CO2 capture and then seawater, we can generate CO2 free gas. So we just emit to the air, which is good. The sodium bicarbonate saturated water will be protonated and generating pure CO2, which can be utilized to carbon capture, utilization, and sequestration. Of course, it has a cost. It's not free, but we are generating desalinated water. Hopefully, the day doesn't come that we need the desalinated water in Denmark, but who knows? So I think it's a very important step forward. To end, I think this is my last slide to thank my group, all the members, and especially this work has been performed in the close collaboration with our spin-off company, CoAPEC. I mentioned that this work recently done by Anand and Alexa, but also previously we have Desta and Alan and other bachelor and master students worked on this project, help to understand this and push further, and other collaborators at DTU helped us the analysis. And also I would like to thank the funding agencies, MUDP and VLUM and DFF for the support, financial support. And I'd like to thank everybody for paying attention for this talk, and I'm ready to answer any questions if you have any. Thank you very much.